Welcome to the Math Worker. For the second week of April for our Weber class, we're refining the area of polygons under in a Cartesian plane. So a Cartesian plane is just a regular plane. It's just a specific term for math. So let's do something simple, right? So let's have something like this. And let's say we have a point here, 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 and here. Okay, so we have this kind of graph. And let's define these as point like 1, 1, let's say 5, 1, 6, 2, and like 3, 2. So how do we find the area under this polygon, in this polygon? Well, what we could do is in if you ever took precalculus or calculus, we learned something called vectors. So in vectors, it's basically lines with direction. So if we have 3 points, we make a vector from this point to this point, and then we make a vector from this point to this point. We call this u and we call this v. Now we draw the same vector right here, which is v, right? It matches this one. And then we draw a vector u from here over here, right? That's vector u. And this makes a parallelogram. So we could find the area of this parallelogram and then we cut it in half, right? We should be able to find the area of the polygon because that's the 3 points that we need, right? So how do you find the area of that parallelogram? Well, what we use something called is a cross product. So we could use the cross product of u and v or the cross product of v and u. It doesn't really matter because it's just two vectors. So using these two vectors, we could just define them as x1, y1, z1, and vector v as x2, y2, and v2, right? Because these are just lines, right? So x1 is the change from this point to this point in the x direction, and then u is the y is the y1 is the change in y direction from x to up the y from this point to this point, and then z is a change in the z direction for this point to this point, right? So it's just for these 2 points for u, x, y, and z are just the change in x, change in y, and change in z. So if it's so for example, if like this point is like 1, 1, 1, and this point is like sorry, is like 2, 3, 4, then the change in x is 2 minus 1 is 1, 3 minus 1 is 2, and 4 minus 1 is 3, right? So the change for so x1 is 1, y1 is 2, and z1 is 3, right? So the reason I introduce is that I'm gonna bring this up later, so we don't need it for now. So we have these two. So what we're gonna have to do is when we're doing cross product is that we set them as I, j, and k. So we have x1, x2, y1, y2, and z1 and z2. And the reason we set it this way is because I is just x, j is y, and k is z. So what we had to do with this is that we had to find the matrix. So it's a 3 by 3 matrix. So but for a 3 by 3 matrix, you could always use the technique to split into a 2 by 2. So then under the I, right? So if we're solving for the I, we could cross out anything under it. So we cross out the x, so we're just using the j and the k. So it's got to be y1. So it's got to be in the matrix y1, z1, y2, z2. Okay, so that's for I. And now for matrix j. So if we're doing the j, we cover up the y's and we do x and z's now. So it's got to be x1, z1, x2, and then z2. Okay, and now we do the coordinate for k. I mean the matrix for k, which we cover up the z's, so we just do x and y's. So it'd be x1, y1, x2, and y2. Okay, so what you need to notice about these vectors is that vectors are usually for x, y's, and z's because they have 3 coordinates, right? They're in the third dimension. But what we're working with is polygons, which is the second dimension. So that tells us that these z's are 0. So if this is a 0, and this is a 0, right? We go replace all these with zeros, right? Z's are zeros. Then what does it tell us about these matrix? So the matrix of I is just going to be 0, right? Because 0 times 0 minus 0 is 0. And then for j is also 0 because 0 times 0 minus 0 is 0, right? But these have no zeros in there, so we don't have to, so basically what these vectors tells us using the cross product to find the area is that we just need to focus on k. So what does k tell us? Well, k tells us is that we just need to put them in order: x1, y1, and x2, y2. So, but remember, I introduced the idea where area of these cross product get the area of the parallelogram. We don't want the area of the parallelogram. We want half of it. So we just want this section. So whatever this k value is, we just do a half. Okay, so we know that is true. So let's kind of delete all this because we don't need it anymore. And then let's interpret this a little bit more. Right, and let's move this over a bit. So basically, this thing, this k value tells us is that we need to take half of the values of coordinate x1, change of x, change of y, change in x1, change in change in y1, change in x2, and change in y2. So what it kind of looks like when we are doing this is that we're going to have to get a bunch of points, which is in this order from x1, y1, x2, y2. So if we want to do more points, more than 2 points, right, then we just have to add more. So we can have x3, y3, x4, y4, right, and then x5, y5, right, etc. But if we had to do that, then basically we could just add another matrix, right, another 2 by 2, another 2 by 2, and another 2 by 2, right? So we could just do a bunch of these 2 by 2s. So why? So then this all accumulates to something called the shoelace theorem. And the shoelace theorem basically tells us is if we kind of choose a point, which I usually like to choose is the upper right, which is in this case 6, 2, right? So that's x1, that's y1. I mean, kind of x1, y1, I'll explain it later. Then we just need to go counterclockwise and choose the points later on. And that's why we have these lines, so it tells us where to go. So the next point is 3, 2, and then the next point down is 1, 1, and next point down is 5, 1. And then we stop when we go back to the first point, so it's 6, 2 again. Right? So we just went around. So the reason we wrote it like this is because we have vectors, right? Vectors, we follow this form x1, y1, x2, y2 in this order, right? So we have a 2 by 2, a 2 by 2, a 2 by 2, and a 2 by 2, right? But remember, these x and y's, these are just the changes, right? So x, these points are all coordinates. We want the change. So 6 and 3 are going to be our change. 3 and 1 is our change, and 1 and 5 is our change, and 5 and 6 is our change. So this is why we're working with we add an extra point right here, 6, 2, even though the last point we have is 5, 1, right? So 6, 2, 3, 2 is this line. 3, 2, 1, 1 is this line, and then 5, 1, 1, and 5, 1 is this line, and then 5, 1, and 6, 2 is this line. So then if we do a bunch of parallelograms with just two of each of these, right? So we're using these two, then we make a parallelogram, then we get the area, then we get this one, right? And then we'll work with the other one, these two, we get this one. And then we add them together to get our area of our entire shape. And that's why we write it like this. So that was just all for explanation. So how do we actually find the area? Well, basically, we write it like this, how I just said it. So we start at the upper right, and then we go around counterclockwise, so we get these points. And then we do a 2 by 2 matrix. So these two, these two, these two, and these two, right? So every single two going down. So 6 times 2 is 12. 3 minus 2 is 6. So that comes out as 6. 3 minus 1 is 3. 3 times 1 is 3. 3 times 2 is 2, so minus 2. That's a 1. So 1 times 1 is 1. 5 times 1 is 5. So minus 5 is minus 4. 5 times 2 is 10. 6 times 1 is 6. So minus 6. So that's 4. So then a negative 4 and 4 cancel each other out, right? So 6 plus 1 is 7. Remember, there's a half in here, so we have to take a half of it to get our area. So our area for this polygon is somewhere 2. And this works all the time for any single polygon. Even if it's like some shapes are like this, and then let's say one right here, right? And then let's say go back up here and then go back here, right? And then we connect all these points together. Even if it's shapes like these are so weird, you could just take this point and then go counterclockwise to get all these points and stop at this point. do the shoelace theorem, and you should get the area. Okay, so this is the general way of how you're going to do it. I hope this video was interesting, and if you like it, maybe check out some of the videos from our other whatever classes. Well, see you next time for the math record.